Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week, a day late after a very crazy and unexpected Friday for yours truly. This is the second time in less than a week that the left front tire got punctured by an object that I simply didn't see coming. One of them was in the middle of the road and one was off to the side, but it just goes to show you that there are roadway demons just waiting for all of us to go over and lose our method of transportation. So, but all that's been fixed now, so hopefully no more sharp objects are in my future. But anyways, we're going to talk today about how the mass of the atmosphere is distributed, and it's actually distributed in what we call a logarithmic sense. So before we delve into that, I thought it would be useful to maybe review what a logarithm is. So let's get into that now. Okay, so what is a logarithm? Well, over on the left there, you see what's called an exponent, which is the number of times that you have to take 10 times itself, okay? Now, you can also look at a logarithm as an exponent, which is the power. It's called a power that you have to raise 10 to get the number desired. So when the exponent is 0, the value is 1. Anything raised to the exponent of 0 is 1. And by the way, you can have any base logarithm you want. Like in this case, I'm using 10, but you could do 2, 4, 5, 7, whatever. And once you establish your base, all you're saying is that's the number of times you have to take that number times itself to get the number that you're looking for, okay? But in this case, 10, and that makes it very, very basic. So anything to the 0 is 1. And then when the exponent is 1, that's simply 10 by itself, so that's 10. And then 10 times 10 is 100, okay? 10 times 10 times 10 is 1,000. 10 times 10 times 10 times 10 is 10,000, all the way up to taking 10 times itself 9 times, and that gives you 1 billion. Now, the exponents are only increasing by 1 at a time, and it's a constant rate of change. But look at the increase in the value of the number that you're dealing with, and you're going from 9 to 90 to 900 all the way up to 900 million, okay? So the value of the number is increasing exponentially. The exponent itself is going up in a very linear fashion, and so that's why we talk about the atmosphere as being distributed logarithmically. So again, a base 10 logarithm is the number of times you have to multiply 10 by itself to the desired number, or the power you have to raise 10 to, and the exponents increase by the same amount, but the number values increase at a much faster rate. Okay, so this is actual data from the Greensboro weather balloon from last night. It was launched at 8 o'clock. And I had to interpolate a couple of these levels because they didn't give me exact values, but it's very, very close. So on the left, you've got surfaces of constant pressure, 1,000 millibars, 900 millibars, 800 millibars, all the way up to 100. And then the height above sea level of each one of those pressure surfaces, okay? Now notice the increase. The pressure increase, or decrease in this case, is constant and linear, 100 millibars. But the value of the number in terms of the height of that surface above sea level is increasing. The difference between 1,000 and 900 is 898. Between 600 and 500 is 1,503. And from 200 to 100 is 4,290. So for the same amount of mass, the same amount of millibars, the 100 to 200 millibar layer occupies 4.78 times the total distance as the 900 to 1,000 millibar layer. So the mass, since density is mass over volume, obviously you've got a much bigger volume, same amount of mass. That means the density is going down significantly. Now, one of the charts that we use in meteorology that shows this very, very clearly is what we call a skew T chart. So let's go on ahead and take a look at that now. And they call it a skew T chart because the lines of constant temperature are skewed. They're not straight up and down or straight across, but they're skewed. And they're skewed because you have a number of different parameters on this chart, and they all have to relate to each other in a certain mathematical way. So that's why the temperature lines are skewed. But we're not interested in the temperature for this discussion. We're interested in the constant pressure surface. So each one of these lines represents 1,000, 900, 800, 700, 600, 500, all the way up to 100 millibars. Can you see how those lines gradually get farther apart? And as they get farther apart, the distance that they're getting farther apart is getting bigger and bigger and bigger, okay? So that's what we mean by the mass being distributed logarithmically. Why is it like that? Well, the closer you are to the center of the Earth, the stronger the gravitational pull, and so the air is getting pulled toward the center of the Earth, and that force is going to be strongest right near the ground or in the lowest few thousand feet of the atmosphere, and it's going to get less and less as you go higher and higher. And so that's the reason why the mass is distributed the way that it is. All right, I hope that makes a little bit of sense. That is bonus weather video number 3 for this week. The next one will be coming up on Monday, God willing, that there's not another tire blowout. And I'm going to have a short version of the daily update this morning to make up for the missed one last night. So hopefully you will find that useful. It's been a very difficult week from a forecasting perspective, and I'll talk a little bit more about that in that daily update. Okay, folks, that's it for now. You all have a wonderful weekend, and I will talk to you again with the bonus video shortly, next daily update shortly, and the next full version of the daily update on Monday. Take care, everybody.